some in our audience will remember that November 1915, 100 years ago, a young physics professor at the University of Berlin introduced a theory that would really begin to revolutionize the world of physics and the way we look at this world in very, very many ways. And of course, that young physics professor in 1915, his name was Albert Einstein, and his picture and his image, of course, are instantly recognizable. Before Einstein came along, or actually even with some of his colleagues, the world of Isaac Newton was the world that was dominant, where everything was predictable, everything was stable. You could look up at the great galaxies, as Newton and other astronomers did, and you could see that gravity had shaped those forces, that those galaxies that looked an awful lot like they were put together by some force, called gravity, of course, were not only just beautiful to look at, but testimony to the force of gravitation. Well, Einstein and his generation were puzzled by some of the contradictions that Newton's predictable, static universe was more or less not able to solve. For one thing, Mercury's orbit kept oscillating on a 3 million year cycle. For one thing, straight lines tended to bend at the north and south poles, didn't they? So there were all of these things that predictable, safe, what we call classical physics, the physics of Sir Isaac Newton and his generation, things were looking a little bit harder to piece together. So what Albert Einstein did, of course, in 1915 was to show how gravity bends light. That light, which was being studied all through the 1800s, was becoming the universal standard of speed and perpetuation and propulsion in the whole universe. It wasn't Einstein who came up with that. Another man named Lorentz, a Dutchman whom Einstein greatly respected, showed that if you traveled at the speed of light, objects would increase, their mass would be infinite, and time would slow down. Einstein built upon that and showed that light bends gravity, and that therefore gravity wasn't alone as the fundamental force in the universe. Now, Einstein had to wait 4 years before his theory became proved by a British expedition that made films during an eclipse of the sun that showed light rays beginning to bend coming out of the sun. So Einstein was a patient and a tenacious person, and he was quite satisfied to wait until his theory was verified that gravity wasn't the only major force in the universe. And by the end of the 20th century, almost all scientists agreed on what our subject really is tonight, the invisible world, that the fundamental forces of the universe, the most powerful forces of the universe, are invisible. We see their workings, but we can't see them at work. So we're going to put up a slide right now of the 4 basic forces in nature. Like I said, this is in a video you can rent from the 1980s by a Nobel Prize winner, pretty standardly agreed upon by most people. And what were the 4 forces? Well, gravity. We see the beautiful ellipse and the beautiful patterns made by the Crab Nebula, the Blue Nebula, the Andromeda Nebula, some of which we already showed. Gravity is a mighty force. But along with gravity, a man named Maxwell, James Clerk Maxwell, came along and showed there was something called electromagnetism. And electromagnetism was something that really was being studied quite fiercely all through the 1800s. And if you look at the atom, which we just did, the atom was finally being fully unveiled by the year 1900. And if you look at the atom, you'll see the electrons circling around the nucleus. And most of us know that from high school. Inside you have a neutron and a proton, a positive charge and a negative charge. And inside the atom, it looks like the atom is all neat and put together, but the space between the circling electron and the nucleus is enough room for a bee to circle a cathedral, you might say. It's sort of a lot of space there that is not able to be reckoned in our models. And so a famous physicist just was trying to explain again to a science reporter how we're all empty space. We are made up basically of atoms which are empty space. Well, then how do we hold together? Through gravity and electromagnetic connections between the electron and the center. Now, the next force you'll see in that slide is something we're very familiar with in our generation, something that Einstein is pretty famous for, and that's force number 3, the strong force. You've got gravity, you've got electromagnetism, and you've got the strong force. Well, actually, we labeled it number 4. The strong force is the power in the nucleus that holds the nucleus of the atom together. And when that force is split or bombarded by other elements, that force gives us an atomic bomb. And when that force and when those atoms are joined together, you get a nuclear bomb. So we're talking about some of the strongest, most important forces in the universe, and most of this has come to our attention in the last 100 years. Now, there's also the weak force that we also had up there, and that sort of explains radioactive decay. If it was just the strong force pressing in, electromagnetism and gravity, the world would become a sludge. We wouldn't be able to move. There'd be no variation or nimbleness. But the weak force balances out some of the strong force so that we're not, stuck in a whirl like this, more or less. So these are the 4 fundamental forces of nature. Einstein's theory, called relativity, showed that what Newton had predicted. Newton said if you just take equations and mathematics and measure them out, you can predict where you will be at a certain time. Einstein said no, the fact that light changes and that mass is affected by gravity shows that our position, if you go far out enough, it's all relative to where you are. And if you travel at the speed of light, strange effects will begin to happen even as you go near the speed of light. Now, nobody can, of course, but not so long ago, the scientists sent 2 atomic clocks. One was on the Earth, and one was sent out in a rocket, and they proved Einstein was right. The clock that went out into space was showing slower time than the clock that was on the Earth. So time, mass, speed, light, these things are all relative. And so these are the big principles that when you look at a picture of a galaxy or a nebula, these are the big pictures that affect the big universe. But in the 20th century, in 1923, even after Einstein's theory, there were some of his colleagues, Niels Bohr, one of them, who was interested in exploring inner space as well. Einstein's teacher, Max Planck, had said that matter was giving off radiation not at a steady rate, but in these short little bursts he called quanta. And so let's take a look at the inside of the atom in a way that nobody had seen it before until Niels Bohr came along in 1923. And I'm going to play you a clip that's introduced and narrated by a Nobel Prize winner named Leon Lederman. And he does a nice job in finally making sense of the phrase you've heard all of your life, the quantum leap. So here's Professor Leon Lederman.
The idea of final certainty bores me to death. Wow. For hundreds of years, physicists have been searching for this final certainty. It was the holy grail of physics. But all that changed for us on July of 1925. It was about 3 a.m. A 23-year-old physicist stayed up all night checking his calculations. He'd found the secret of the atom. He said it was like peeking over the shoulder of God to see how the universe was made. What he saw changed physics forever. The guy with a hat has gone home, so let's see if I can do this myself. Why does the screen glow? Why does anything glow? The answer lies in electrons, which is what our 23-year-old physicist was studying. Atoms emit light when electrons jump from a higher energy state to a lower energy state. In this transition, light in the form of photons is emitted, particles of light. With that knowledge, we've been able to fill the world with lasers and television sets and fluorescent bulbs and everything that creates light. But even though we can make these things, our physicists realize that we will never be able to know how an individual electron behaves. Complete certainty about such a simple and fundamental fact could never be known. Instead of certainty, we would have to live with uncertainty. And that, ironically, was what revolutionized physics. It was the big discovery. Started with a search for a new model of how an atom works. This was the old model. Atoms were seen as little solar systems, electrons orbiting the nucleus like planets around the sun. It was a seductive idea. Perhaps the largest and smallest parts of the universe were mirror images. But electrons aren't like planets. An orbiting electron would lose energy and collapse into the nucleus in just billionths of a second. Pow! Electrons don't really behave this way, and it's a good thing they don't. It takes atoms billions of years to form the galaxies and stars and planets, not to mention us. Something was wrong with the theory. And it took this man, Niels Bohr, to find part of the answer. In Bohr's atom, electrons disappeared from an orbit and reappeared in a different orbit without crossing the space between. These mysterious jumps became famous. They were known as quantum leaps. And in 1922, Niels Bohr won the Nobel Prize in Physics. Bohr became the new king of atomic physics.
Welcome back, everybody. This is Neil Earl with a second look. You just saw a video clip of Professor Leon Lederman, a Nobel Prize winner, showing how the world of physics, the world of science, completely overturned and moving in strange directions because of the work of Niels Bohr and his colleague and sometimes debate partner, Albert Einstein. The year 2015 was the 100th anniversary of Einstein's general theory of relativity. And basically what that showed was that the very predictable and cozy universe of Isaac Newton and all of his other generation that they could measure and predict where people would be at certain times no longer applied when you added the factor of light and the speed of light. That at the speed of light, objects would expand and time would slow down. Einstein looked at the big picture outside the Earth. He looked at the big universe. Niels Bohr chose to look inside the atom. And although Einstein knew about the quantum, from his professor Max Planck, his hero, this began to change things and shake up the world of physics. Einstein couldn't believe that the atom was so unpredictable, that the electron, you just couldn't tell where it was going to be. And he made that famous statement to Bohr, God does not play dice with the universe. And Bohr replied, Einstein, stop telling God what he can't do. So you had these interesting interpersonal dynamics. So relativity began to expand and greatly mystify, in some ways, the settled world of mathematics and Newtonian, and even going all the way back to the Greeks. Newton's world of straight lines and calculations. Now we are in a quantum universe, and that was going to change a lot of things. And the theory was called relativity because it showed if you were in a different place in space, things might look and act differently. Now this begins to introduce the invisible world even more. We knew from the atom that the world was invisible. And I'm covering this as a minister because when I teach Bible class to teenagers, they get harassed sometimes for believing in an invisible God. And I say, everyone believes in the invisible. And all I have to do is show them a picture of an atom. We can show you one now. And that will sort of give credence to the fact, of course, that you do believe in invisible things. And not only are things invisible inside the atom, they are very mysterious and strange. What I'm going to do now is play another clip from Professor Letterman. He won a Nobel Prize tracking down some of these particles inside the nucleus of the atom. Can you believe? I used to show my diagram of the atom, but if I'd only known how mysterious, how novel, and how unpredictable the structures inside the atom were, I would have really had something to work with. But I'm going to show it to you instead. So here's Professor Letterman showing how strange and mysterious the world is inside the nucleus of the atom.
To underline how different it is, let's put a marker to indicate an elementary particle. Nice marker, but why does it look like that?
Well, it's like an astrolabe, navigational device used for finding position. Astrolabes pointed into outer space, and this marker points to inner space, and it lets us see the particle's name and its mass. It points to where the particle would be if we could see it.
Right. Now, the electron isn't the only elementary particle. To find the others, we spent years smashing protons together in accelerators. We found thousands of new particles. Many of them hadn't been seen since the hot, early days of the universe. But in all these collisions, we found only 5 elementary particles like the electron. They were given special names like muon neutrino and the tauon. Now it was possible to start building a family portrait of the particles that make up the universe. These 6 particles are called leptons, Greek for something fast. The heaviest one on the right is 4,000 times more massive than the electron. Strangely enough, they come in couples. It's such a sweet symmetry. The bottom 3 are called neutrinos. My Nobel Prize came from discovering this one. Neutrinos are produced by nuclear reactions in the sun, and there are millions of them that pass through our body every second. Neutrinos are also produced in accelerators. In our experiment, we had to build a wall of steel 40 feet thick.
How much did that cost?
Not much. We used the scrap from an old battleship. But leptons are only half the story. Let's look at the other half in the nucleus. We're heading for the nucleus of a carbon atom. It's made of 2 types of particles. Those red balls are neutrons. They have no electric charge. The yellow ones are protons. They have a positive charge, which is why electrons are attracted to the nucleus. The protons and neutrons make up almost all of the atom's mass. But what are they made of? The answer lies inside. And what we find are the weird brothers in the family of matter. These 3 are called quarks. They're odd because they always come in clusters. No quark is ever alone. This quark is called up. There are 2 ups in every proton. They're joined by their other brother down, that one at the bottom there. These 3 point-like quarks spin and quiver, making one very solid piece of matter, the proton. It's an odd system, but it works. All protons and neutrons are made of the up and down quarks. So now we can finally finish our family portrait of matter. The 6 leptons are joined by the up and down quarks. Although they're the most common quarks, they're actually the lightest. They do have much heavier cousins, the charm and strange quarks, and the extremely rare bottom and top quarks. My colleagues and I discovered the bottom quark back in 1977.
So, charm, strange, top, bottom, quark. What's with the names?
Well, you can blame the theorists for that. Experimental types like me try to prove they exist. But quarks were different. They were like nothing else, and their discoverer, Murray Gell-Mann, picked the word out of a line from James Joyce's Finnegan's Wake. The rest of the names were whimsical names which somehow seemed appropriate to the particles themselves. So there you have it. The family portrait of matter. 3 generations, 12 particles in all. And the universe is what they create. The physicist Niels Bohr once said, "When it comes to atoms, language can only be used as poetry."
The poet, too, is not nearly so concerned with describing facts as with creating images.
Welcome back to a second look. We're here on the 100th anniversary of Einstein's theory of general relativity that dealt with the workings of the great masses of the suns and the galaxies in outer space, and how the speed of light had to be added to mass and matter to be able to make sense of it all, and sort of overthrew the stable, predictable, mathematical clockwork universe, I call it, of Sir Isaac Newton and his colleagues. And Einstein, of course, had a great friend called Niels Bohr, and it was Bohr who began to delve inside the atom. And after World War II, scientists had the freedom and the luxury and the resources to be able to study these strange things that are unpredictable inside the shell, you might say, of the nucleus of the atom. As a matter of fact, the inside of the atom is so strange that one British science journal said, after quarks, the virgin birth is easy to believe. After quarks. And Letterman showed you how strange these creatures were, dancing and spinning around inside the nucleus, the electron attracted by electromagnetism around the heart of the atom, which makes seem like we're solid space, but most scientists are quite clever to tell you that we're made up of empty matter, unfortunately. So here we are. What does all this mean? Well, there was a scientific-minded theologian in Scotland who was watching all of these observations from science. His name was Tom Torrance, and he studied the words of men like Professor Lederman, whom we've just quoted. Most laymen, when they read the LA Times science page, aren't aware of how complicated and mysterious the universe has become. It's become more mysterious, more baffling, even though we keep uncovering more useful ways to deal with it. Well, Lederman said the frontiers of science are filled with uncertainty and even confusion. Every step forward is accompanied by new mysteries. And when you look at quarks and what goes on in their world, you begin to realize what's behind all of this. What's behind all of the forces, the 4 big forces we talked about at the beginning of this talk. And now the strange quark structures that are going on and the neutrinos that bombard us millions of times from the sun. What is going on? Well, Tom Torrance, whose picture we'll show you here, Tom Torrance in Scotland began to realize that what science was uncovering, what physics was uncovering, was a universe that was open to newness, a universe that was open to mystery, a universe that was open to surprises, that things weren't all said and done. Every hair wasn't in place, that not everything could be pictured mathematically. The quantum, for example, all we could do was arrive at certain guesses as to where those quantum particles would end up. This whole science of particle physics is a real head scratcher for many people. So Torrance, looking at it the way I began to teach it to kids in Bible college, began to realize that most of the forces and most of the things that govern our lives, the neutrinos that are going right through our body right now, most of these forces are invisible. And the Bible had said centuries ago, and I'll show you the scripture, one of the scriptures we'll put up there on the screen, that God ruled over not only the visible world, but also the invisible world. And that the world that we see is not made out of visible things that we can measure and calculate, that it's actually stemming from something that was created out of nothing, that the visible world comes from the invisible world. Those scriptures like Hebrews chapter 11 and Colossians chapter 2, verse 16, you can look at these as we put them up there on the screen. So Torrance was the scientifically minded minister, you might say, who began to realize that now, after Einstein and relativity, Niels Bohr and quantum mechanics, that almost the sky was the limit, that the frontiers of science were open, they were not static, everything could not be accounted for logically, systematically, and scientifically. We had to take things on hunches, on intuition. The way penicillin was discovered in the 1920s when a man left a spore of bacteria out overnight, things that happen, accidents. The Big Bang Theory, when men working for General Electric were trying to, get their big telescope set up, and they thought New York City was making all this hissing sound. It wasn't. It was this background cosmic radiation, discovered almost by accident. Intuition and hunches. We've all heard of Newton's apple and James Watt's steam kettle. And so this led to a world, Torrance thought, that was much more congenial to those who believed in God, that there was a master mind behind everything, holding all of these forces in place, not only holding them in place in an organized way, but also inside the nucleus of the atom in a playful, almost joyful way, with all of the strange things about quarks and their names that they're given up and down, and some people say the particles inside the atom remind them of characters who fight in the novel Lord of the Rings. That very well could be it. I'll end off now making my point, and my main point has been in this show, The Invisible World, that perhaps the most dramatic and dynamic things in this universe are invisible after all. Hebrews 11 says, verse 3, "Through faith we understand that the worlds were created by the word of God, and the things which are seen were not made of things that do appear." Well, this Bible is not a textbook in science. It's not a physics book. It doesn't explain relativity. But it may go farther than some people think to explaining the God behind relativity, quantum theory, and the four major invisible forces that make this universe work. It's something to think about on the 100th anniversary of the announcement of the theory of relativity. Okay, I'm Neil Earl. See you next time on A Second Look.